Hello friends, in this video I'd like to solve the following problem for the Korean Mathematical Olympiad final round 1993, problem number 3. We wish to find the smallest positive integer n such that 7n to the power 25 minus 10 over 83 is an integer. Okay, this problem is not that difficult, but it's rather lengthy. We will have to make use of several facts from number theory. First of all, Fermat's little theorem says that if a is an integer, p is a prime, and p doesn't divide a, then a to the power p minus 1 is congruent to 1 modulo p. That's the first fact which will be useful. Second fact, Bézout's identity says that if a and b are integers, which are both not zero, then there are integers x and y such that ax plus by equals the greatest common divisor of a and b, GCD. And moreover, this x and y can be found in rather effective way by the extended Euclidean algorithm. And moreover, we will be left with something in the end we will have to find n to some great power modulo 83, and the fastest way to, for humans at least, the fastest way to find x to some great power modulo 83 is to write x in binary system and then consecutive squares. So find n modulo 83, then n squared modulo 83, then n to the fourth power modulo 83, and so on. That's the quickest way to find n to the power of x. Okay, so give this problem a try, and I will see you in a minute. Okay, so here's my solution of this problem. So first of all, let's notice the following, that 7a to the power 25 minus 10 over 83 is an integer. It's pretty obvious if and only if 83 divides 7n to the power 25 minus 10, which in turn is equivalent to saying that 7n to the power 25 is congruent to 10 modulo 83. And now I wish to eliminate this 7 from the left hand side, and you can do it in various ways, but the fastest way is to multiply both sides by 12. It is possible because 12 is co-prime to 83. And notice that 7 times 12 is 84. And 84 is, of course, congruent just to 1. So we wish, in other words, we wish to solve this congruence. How can we do it? Well, the crucial observation is Fermat's little theorem. Note, namely, that 83 is a prime. 83 is a prime, which means that by Fermat's little theorem, n to the power 82 is congruent to 1 modulo 83. And now the idea is, by Bézout identity, there are integers x and y such that let's say 25 times x plus 82 times times y equals 1 because GCD of 25 and 82 is 1. And conceptually, think about it. If this is true, then n to the power 25x times n to the power 82y equals n, which means that it's congruent also to n modulo 83. But by Fermat's little theorem, this is just congruent to 1. So n to the power 25x is congruent to 1 modulo 83. And remember that n to the power 25 is congruent to 120. So 120 to the power of x is congruent to n modulo 83. Now, only two things are left. First, we need to find this x, and then we'll have to manage this large number. First part is easy. Finding x. How can we find x? As I suggested, it can be found manually without using of calculator or computer algebra. It can be done by extended Euclidean algorithm. Extended Euclidean algorithm. I will do it to demonstrate you. So let's start with Euclidean algorithm. We want to find, we have two numbers, 82 and 25. And we will divide with remainder 82 by 25. If you do it, it's just 3 times 25, and the remainder is 7. And now we'll do the same, but with 25 and 7. 25 is 3 times 7, which is 21, and remainder is 4. And again, now we will take 7 and 4. 7 is 1 times 4 plus 3. And finally, 4 is 1 times 3 plus 1. And this number 1 is the GCD. That's just the standard Euclidean algorithm. And now, extended Euclidean algorithm allows us to find x and y in the following way. So, from the first equation, let's notice that this number 1, it's 4 minus 1 times 3. Okay, but what is 4? No, what is 3? 3, by this identity, it's just 3 is 7 minus 1 times 4, which is to say, after simplification, it's 2 times 4 minus 1 times 7. But what is 4? 4, by this identity, 4 is 25 minus 3 times 7 minus 1 times 7. And here we have, what exactly? We have 2 times 25 minus 7 times 7. And finally, what is 7? 7 is 82 minus 3 times 25. 82 minus 3 times 25. And that will be Minus 7 times minus 3 is 21. 21 plus 2 is 23. Maybe write it in, I don't know, think 23. And here we will have minus 7. Am I right? I'm probably right. 7 times 82. Okay, very nice. Remember that these are our numbers x and y. Let's go back. 25 times something plus 82 times something is 1. This is x, this is y, and this is 1. Very nice. And now, what we need to do, now we know that x equals 23. So, going back to this condition, which I will mark asterisk, we now know that n is congruent to 120 to the power 23 modulo 83. So our condition asterisk becomes the following. N is congruent to 120 to the power 23 modulo 83. Okay. And now the rest of the video will be simplifying this expression. Or maybe let's do one more thing, because 120 is congruent to 37 modulo 83, because 27 plus 83 is 120. So we wish to find this number. How can we do it? Well, as I suggested, let's write 23 in binary system. 23 happens to be 1 plus 2 plus 4 plus 16. And now that means that 37 to the power 23 is congruent to 37 times 37 squared times 37 to the fourth times 37 to the power 16 modulo 83. And now we just need to find these numbers and reduce them. So, well, 37 is 37, nothing to be done. 37 squared is 1369, and that is congruent to 41. 37 to the fourth power is congruent to 41 squared. And 41 squared is 1681, and that is congruent to 21 modulo 83. What is 37 to the 8th power? 37 to the 8th power is congruent to 21 squared. 21 squared is 441, and that is congruent to 26 modulo 83. And finally, 37 to the power 16 is congruent to 26 squared, and that is congruent to 676, and this is congruent to 12. Okay. So, now we know that implies that 37 to the power 23rd is congruent to 37 times 41 times 21 times 12 modulo 83. And I will leave the boring multiplication to you. You know, multiply it, reduce modulo 83, and so on. It will turn out that this product is congruent to 69. And that means that our number n is congruent to 69 modulo 83. Very well. And we are almost done, because let's go back once again. What we want to find? We want to find the smallest positive integer such that this congruence is true. So the smallest integer, of course, is just 69. So let's write it in yellow or in green. The smallest integer, the smallest positive integer, n, such that n is congruent to 69 modulo 83 is obviously, well, 69 itself. And that is our answer. So, a pretty nice problem, I'd say, because we have used Bézout's identity, extended Euclidean's algorithm, and Fermat's identity. Classic problem. Thank you for watching, and I will see you next time. Goodbye.